So anyway, so you got x of 0, x of 1, x of 2, like that, you know, x of n. Okay. Now, what are these numbers?
So those are the samples representing the actual value of that voltage of that signal at that time.
At that time, right? And if you look at the nature of this analog signal, it is bounded, let's say, between above and below.
Yes.
And it can take any value.
Yes, of course.
Right?
Now we have a problem. I can see where you're getting at. You now need an infinite number of points, amplitude values as well.
Yes.
Okay, so we have a problem.
Right? You have a problem. So I cannot say x0. Okay, if I were to represent this up to 1000 decimal places, right? 1.2394.
Yes.
Go all the way. Next one is 2.3478. Some 1000 decimal. It's not possible.
Yes.
But in reality, the analog signal is like this, right? What do we do?
We should do the same thing we did in the time domain.
Exactly.
Right?
Yes.
In the time domain, we changed that infinite value to some finite number of points.
Yes.
So we should do the same thing in the amplitude
exactly.
as well.
So we did time quantization. Now we need to do amplitude quantization. Okay.
Great.
So this is what leads us quantization. Okay.
Okay.
And what that means is we are now not going to deal with real numbers. So let's say,
is this that bit that you are talking, that the other?
That,
right?
exactly.
That 16 bit is what it said.
Exactly, right? 16 bits we'll come to because that requires a binary representation. But first we'll just look at it from x0, okay, to xn. Let's say that these values were real numbers between 1.2 and 3 or let's say 2.5. Okay?
Okay.
So it spanned a voltage range of 1.3 volts.
Okay.
Now the actual representation, okay, if you take, you know, this is 1.2 volts and then this was 2.5 volts. This gap is 1.3 volts. It could take any real number between this.
Yes.
Now what we are saying is we are not going to do that. We are going to quantize this into some fixed number of values.
I see. Okay.
Okay. And let's say this amplitude quantization is some m levels, 0, 1, 2, 3 all to m minus 1. Okay. So first thing what we need to find out is what is this delta?
Yes.
Right? What is the delta? So the delta, if I have m levels,
yes,
right? So m into delta should be the range of that.
That's right.
Right? So
that's right.
That is the 1.3 volt that we have in this case.
Yes.
Okay.
So delta is the distance between the levels. I have m levels.
M levels.
Right.
Okay. So delta is going to be 1.3 by m. Some m levels.
Sure.
Right. So what this means is.
Got it. So just like I had a time period t for which I was recording, I am dividing that by the number of samples to get the time period for each sample.
Correct.
Okay. So this
same
is
thing that
same thing we are doing in the amplitude
okay.
domain.
Yeah. So what does this mean? It means that if this is 1.2 volt, then the next one. So let us pick a nice. Let's say we have 130 levels.
Sure.
Because I have 1.3 volt. Okay. I'm just
easy.
going to easy. Yeah. Okay. So I'm going to say m equals, or I go to the next page. Okay. I'm going to say m equals 130 levels. Okay. And my range 1.3 volt. Okay. So this was
1.2,
1.2 and 2.5.
yes.
Okay. And then I have broken this like deltas like this. So if this is 1.2, then the delta, okay, for 1.3 and 130 levels is 1.3 volt divided by 130.
Yeah.
So I'll put that in millivolt. It is 1300
1300 by
millivolt
130.
divided by 130,
Yes.
right? And that therefore that's going to be 10 millivolt.
Yes.
Okay. So if this is 1.2 volt, which is again I'll translate that to millivolt.
Yes.
1200 millivolt all the way to 2500 millivolt.
I see. So the next one, the next level will be at 1210 millivolts.
Exactly.
I see.
1210 millivolt. 1220 millivolt, right? 1230, right? So this will be 2590. No, 2490.
2490. Okay, I see now. So
Yes.
which means if I quantize it like this,
Yes.
if I took a sampling, so I'm now trying to tie back to what you did in the time, in the discrete time.
Yes.
If I took any one of those x of 0, x of 1 all the way to x of n times ts is what you wrote.
Yes.
They will lie between on any one of these lines.
They will lie somewhere here.
Somewhere
so
here.
For example,
And if you decide to do amplitude quantization, you are going to tie it to the nearest level?
yes.
Is that what you're saying?
So let's
I
say
see.
this happened to be x of 0.
I see. Okay, so it lies somewhere here in the space.
Somewhere. Okay.
Yes.
Yep. It's not on these lines.
It's not on these
It can
lines.
be anywhere in between.
I see.
Okay.
Got it.
But
because there are an infinite number of points to
exactly.
occupy.
Exactly. This
Yes.
might be x0. Remember that, you know, when I go back and see my signal here, the same x0 value will come back for x2.
Absolutely.
So everything sort of pigeonholes back into these bins.
Yes.
Okay.
Yes.
So therefore, this is, you know, x of 1, x of maybe 6, something.
Sure.
Right. And somewhere here might be x of 700, right? X of 650. Doesn't matter, right?
Understood.
Every value will fall in this range.
1.2 to 2.5.
Exactly. And they are going to lie between two bins.
Yes.
So what do you suggest we do in order to
If I want
represent?
finite number of points.
Yes.
Right? The problem is right now they are still infinite because they lie anywhere in the space.
Exactly.
It seems like what I would do the minute I have these levels, maybe I should tie it to the nearest possible level.
Nearest possible level.
Like a round off error.
Yes.
So in other words, you showed the decimal, right?
Yes.
Having infinite number.
Yes.
I'm not going to round it off to the nearest decimal
Exactly.
accuracy.
Right? That's what we're going to do. So what we're going to do is we're going to say this x0, x1, x6 lies. So I will say any value between 1210 millivolt and 1220 millivolt, I'll simply tie it, round it off to the lower limit.
Sure,
it can
let's
be
go
anything.
to the lower limit.
Okay,
Yeah.
so this I'm going to call it as 1210 millivolt.
That's like truncation.
Truncation, exactly.
Right?
Yeah, truncation, round off, it doesn't matter, right? There are different strategies, but I think they are all equivalent
They are
in
all
some
equivalent.
sense. Okay. Likewise, 700, 650, anything between 2490 millivolt and 2500 millivolt, I will tie it to 2490 millivolt.
Okay.
Right. So the maximum that we can have, if you look at it, right? So we have x of nts. Okay, the nth, small nth sample, okay, we are going to quantize this as xq of nts.
I
Okay.
see. Okay.
The only difference between x of nts and xq of nts is that x of nts can take infinite real number values,
Okay.
xq of nts can take finite number of
I see.
values. These are not integers, by the way.
I
These are not
understand.
necessarily integers. These, if you look at it in volts, it's 1.21 volts,
Got it.
right? Nothing is an integer or something. It is
Understood.
just a bin that we have sort of
Got it.
pinned it to.
So there is some error now.
Yes.
Which we are introducing.
We are introducing,
Right?
Right?
Because by doing this, tying it to the lower side, we are now introducing from the actual value versus this.
Exactly.
I see.
Right?
Okay.
So that sort of, you know, brings us back to the discussion I had with Bobby, right? If I asked you the value of E,
Yes.
your first question should be how many digits of decimal do you want?
That is true.
Right?
That is true.
Then I don't need the infinite Taylor series. I stop at the fourth term, right? And therefore, I can represent that number E to the required precision level, okay? But sufficient for my operation.
Understood.
Okay?
Perfect. Perfect.
So, and just going back to your discussion on the time, the intuition that you gave on the time, if you do enough number of bins,
yes.
right, you are closer to
You're
the real
close enough.
value.
The error
right?
will be very small.
Exactly.
Right?
Okay.
Right.
So therefore, yes, so the xq of NTS, these are now finite values.
Understood.
Okay. So can you help me now, sort of plot, if I were to look at x of NTS, okay, any sample, and xq of NTS, okay, and in general in signal processing we tend to drop this TS because we know it's a sampling rate, that's
Correct.
a constant number.
Correct.
So we will refer to this as x of n and xq of n.
Correct.
Okay.
Because the sampling rate is what is constant, right? In some sense, that
Exactly.
is that TS that you wrote.
Yeah, right. For that channel, we know we fixed it at some 8,000 or 44,100, right? So if I were to now look at, okay, x q of n, okay, versus x of n, okay, and now I can drop this n also because for every sample we are going to do this.
Yes.
Okay, so if I give, what I am saying is I have a block that does quantizer.
Yes.
Yeah, I'll call it amplitude quantizer.
Yes.
Okay. Okay, I give an x, I get an xq, and I want to just look at
Understood.
where it is going to happen.
Right.
How will so this is what we call a transfer function.
Yes.
The output is xq, input is x, I am plotting xq versus
the transfer characteristics of the quantizer.
that block.
Of
Yes.
that block.
So what do you think it will be?
So first of all, this x of n was the unquantized, the raw values.
Yes.
That had infinite number of points.
Yes.
So it seems like actually the x-axis I am varying infinitely,
Yes.
right?
So
It's continuous.
exactly. So it could go all the way.
In
right?
our case from 1.2 to 2.5.
Exactly. So maybe we'll start it here like this.
Okay.
1.2 to 2.5
Okay.
volt, and we'll say this is in volt.
Sure. Why
Okay,
not?
or millivolt, right? I'll change that to 1200.
So 1200 to 2500. Okay.
Yes.
Okay.
Now, xq is going to get quantized. So what will
Yes.
happen?
Can you go back to the previous page?
Yes.
So what I'm seeing is you said anywhere it lies
Yes.
between two levels, you're
Yes.
going to tie it to the lower side.
Yes.
Which means anything from 1200 millivolts to something just less than 1210 millivolts,
Yes.
it's always going to be 1200,
Yes.
right?
Yeah.
So which means when from x equals 1200 to x equals 1210,
Yeah.
the xq is always going to be 1200,
Exactly.
right? Maybe we can draw that
So
first.
I'll just, the equivalent of these horizontal lines are vertical lines here because our x is,
That's right.
okay. So just to sort of set that thing right, this is how it looks.
Yes.
And then I want to break this into small deltas.
Yes.
Okay. Sorry. Yeah. So now you're saying if x, and this is 1210 millivolt,
Yes.
this is 1220. Okay, I can drop the millivolt actually because the axis is marked, right? This is 1230 and so on. Right?
So maybe what we will do, even on the y-axis, right?
Ah.
Maybe we should start marking 1200, 1210.
Yes,
right?
exactly. Yeah.
Maybe we should do that as
Okay.
well.
So then, we are going to look at, so the xq
Yes.
can again take values between 1200 and 2500.
Correct.
So there's no change there.
Yes.
Okay.
Yes.
So this is 1200 and
2500. I
maybe
guess.
I give myself a little more space, and yeah, 2500. This also is in millivolt. xq.
Okay.
Okay. So now you're saying anything between 1200 and just less than 1210
Yeah.
was going to come out.
Maybe we can draw it in blue or something like
Yeah,
that. Transfer
absolutely.
characteristic
Yes.
to highlight it.
Yes, absolutely. Right. Was going to come out.
Yes.
So any input between 1200 and 1210
Yes.
was going to get truncated to the lower value.
Yes.
And therefore it would look like this.
Yes. Yes. Correct.
Now I hit 1210.
immediately it changes to, I think, to the next level.
To the next level.
1200 plus delta, which was 1210.
1210. Okay. So therefore, I have 1210 here. Okay.
Yes.
Okay. Right. So maybe this one I should, I'll actually draw this in a different color because
I think that's a good idea.
Yeah, because I'm just using this to mark the axis.
Yes.
It's not it's not part of the transfer characteristics. Okay. Yeah. The blue is what I'm going to. So now we hit 1210. Anything from 1210 to 1220.
It will always give you 1210.
Yes. Okay. So it will go up abruptly and give you this
yes
value. Now I hit 1220. It has to make another abrupt jump to 12.
Looks like a staircase.
Exactly.
Right?
Yes. Right. So this is the staircase that electrical engineering is built on.
Yes.
Right?
That's right.
And it goes all the way like this. It will just keep going. How many ever levels there are, all the way to the final output. Okay. Maybe I will draw that carefully. Yeah. Okay, so this is what we call a.
So the final one will end at 2500, I guess.
Will end at. Oh yeah. Sorry. You are right. It will end at 2500. Yeah. So I think I need to. The slope has to be adjusted.
That's okay. I think so the idea is understood.
Yeah. Okay. So in fact, I'll actually leave some gap here because it goes like this, and then. So will it end at 2500 or 2490?
In our case, it ends at 2490.
Exactly.
So we should be careful.
It will go to 2490.
Yes.
And then the previous bin will be 2480. Okay.
Correct.
And so on.
So in fact, I'll now make a guess.
Yeah.
So now I could say, even if the input went to beyond 2.5,
yes,
maybe it went to 2510 or 2520.
Yes.
The output will still give you only 2500 because we said you're going to just, these are the maximum values.
Correct.
So can I extend this curve beyond like that?
So what happens? Correct. So
probably I could, just for the conceptual drawing.
Correct.
Because
so I will say
we only have finite number of points.
It's going to freeze like this.
Yeah, it's just probably going to freeze like that, I guess.
Just continue like that. Right. We are assuming that your inputs are constrained.
That's true. You made a statement right at the beginning that the inputs are bounded. Between 1200 to 2.5.
Exactly, right? And therefore, if the input is out of this bound, then this quantizer is not expected to work. Okay, yeah. So that's how any electrical engineering product, there is a spec. If you are within the spec, it will work.
Yes.
Outside that, all bets are off. Okay. Yeah. So now what we have is a finite set of amplitude wave, finite set of time values, finite set of amplitude values.
So each one of those time points is also converted to this finite set of amplitude points?
Yes. Okay.
I see. Okay.
Is converted to, So in some sense, now what you can do, right, is, okay, in this experiment, it was 1200. In another experiment, it may have been from 2500 to 3000 something, whatever, right? But maybe I can remove this bias of this 1200 and just represent this as 0, 1, 2, 3, right? And
simple, yes.
Right, go all the way to 130 or something like that, right? Or 129, actually 129, right? So this one is, maybe this I will write in a different color again because I am saying, I am doing a remapping now, okay? I will call it 0, 1, 2, 3, all the way to 129. So now our x of n, xq of n, I'm sorry.
xq of n is now
is
abstracted to numbers.
L is one of the numbers 0, 1, 2, all the way to 129.
Perfect.
Okay. So
this is amazing.
Right?
Right.
So if you take our that audio waveform that we had now, t, right, and you look at x of t about, we discretized in time,
yes,
we got a value, we discretized in amplitude, we got xq of 0.
Yes.
And what is this number? This will simply say 0 or 1 or 2 or something. So
it's amazing.
That integer would actually mean some particular voltage that depends on the bias, on the range, and everything, right?
Yes.
And then this one is going to be my x q of 1, right? So if this is, for example I say this is 0, then this might be 1, right? Then this might be 2, right? 3, then you're back to 2, back to 1, you know, like that you go down. Yeah. So maybe the lowest point is what I have to call as 0.
Yes,
right?
that's
so
right.
So maybe I have to call all this as maybe somewhere through 65.
Yes.
65, 66, 67, 68, then it's back down. Somewhere here it might be 0, right? Or this voice signal was even lesser than 1.3 to 2.5 volt, right? Whatever it is.
Yes.
Some numbers. Now we are one step closer. I think now we can safely say we have finite number of time points, finite number of amplitude values.
Yes.
Somehow we can store these numbers,
Perfect.
right? So therefore I can, if I were to just look at this wave file, right, I would tend to store this just by these integer values, 65, 66, 67, 68, back to 67, 66.
Yes.
And a sequence of numbers like this.
Okay.
The last one is our x of n ts or n minus 1 ts, whatever.
Yes.
So you know, have you.
So what I get at the end is just a number.
Yes.
And some timestamp. That's all I need.
Yes,
exactly.
This
is amazing.
Right. Now, if you were to sort of, you know, these are all what do you call, the representations needed for the computer, but when I played back on a speaker, right?
Yes.
I need to take these things back to the voltage domain.
That's right.
Right?
That's
so
right.
what would you do? You would then take this 65 number, look at it as, okay, it started with 1200 millivolt.
Yes.
You add 65 deltas to it.
Yes.
Which is what, 10 millivolt?
So 650 millivolts.
650 millivolt, right?
Yes.
65 into 10 millivolt.
Yes.
And then you will get what, 1850 millivolt.
Amazing.
Then this would be 1860 millivolt.
Yes.
Right? 1000.
So I can completely get back something very close to my original signal.
At least the quantized voltages.
The quantized voltages you can get
back, right? And then you go back and feed this to the speaker, right? Like the argument you made on time, if you have sampled densely enough,
yes,
it's going to approximately play the same.
Makes sense. So it's to do with how good your ear is.
How good your
ear is. So this is what you meant, right? When MP3 compression, you said that the music directors don't like it.
Exactly.
With the original quality versus the compressed quality. I see.
Exactly. Okay. The music directors have a much better ear.
Much better.
Right?
Ear.
That's something that we cannot even perceive. They will actually be hearing, right? So effectively, what we have seen is, we have, you know, in order to take something into a computer, we had to discretize in time, discretize in amplitude, and then undo those when we wanted to come back to the real world.
Yes.
Okay. So these things have a name, and maybe it's a good time to introduce the students to this thing. Okay. So the amplitude quantization is what they call the ADC, analog to digital conversion. Okay, what we have done here now, by the way, is not yet digital conversion. We have only looked at discrete conversion. So this is something we are yet to discuss. What we have done is analog to discrete amplitude.
Yes.
Right?
Yes. We still don't know what that digital is. Correct.
Okay. Discrete amplitude conversion. This is what we have done, and that's called an ADC, right? Likewise, the opposite of this, taking the amplitude quantized value and pumping it out back as real world voltages, right, is called DAC.
Digital to analog conversion.
Exactly, right? So this is digital to
So are you telling me
yeah.
that you showed me Audacity, this microphone went into your computer?
Yes.
Are you telling me that the computer sound card has an ADC and a DAC?
Absolutely.
I see.
Absolutely.
Okay.
That's the first thing that a sound card has to do.
I see.
Right.
Okay.
In fact, most of these real world applications have to do that. Right. You need an ADC. It can be any other sensor also. If it has to go into a computer, it has to first meet an ADC.
ADC.
On the way.
I
Right.
see.
And that's why that is so central. So in fact, whatever you saw here, right, this staircase waveform that we plotted was essentially the transfer characteristics of an ADC.
I see. Okay.
Okay. So I think with that, we have been able to introduce students, and since you brought up the topic of a sound card, right, we will look at a sound card later. Okay.
Okay.
But I will also show you here, right. You just go on Amazon and search for sound cards, and you will get a whole lot of them. So what you see is, if you blow it up, you see these 3.5 mm jacks.
Those are the analog inputs.
Yes,
I'm sure. Okay.
right, where you can actually, go and plug in your jack, right. In fact, this may be a good time for us to remove this, and if you see this
Yes.
thing, right. So let me just show you that. This
Yes.
jack,
Yes.
right. This jack, okay, is essentially what we call the 3.5 mm jack that will go into one of these ports here, one of these ports.
Okay.
Okay, and then there are various ICs on that, right. So if you go look at, what does this particular creative sound card look like, it has a lot of things, but you scroll all the way down. One second, or actually you just look for the word ADC.
I
You will see on the audio path,
Okay.
it will
There's
say
an ADC and a DAC.
ADC 24-bit. Now that is what you mentioned earlier,
Yes,
the
yes.
16-bit, right? Though we have not yet discussed it, it seems to be tied to this ADC business. Okay, so this is an ADC, and now there is a DAC.
DAC.
Okay, and with this you can go into the computer and come out of the computer very easily,
Perfect.
right? So in the next lecture we look at these ADCs and okay, how do you actually, at least in principle, what is needed to implement an ADC and so on. Okay.
Okay.
Thank you.
Yeah. Thank you.